Welcome to this workshop. Yeah, I'm happy to meet so many interested colleagues in this topic. Um, and yeah, and yeah, I wanna start with a nice image from the Danube River landscape in Vienna around 1718. As you can see, it's a typical, let's say we say it's an unbranching river system. It's not a braided one because unbranching system have show large vegetated islands separated by several river arms. And we can see some human infrastructure already. Here is the bridge crossing the Danube River of one of these arms, but we can see also here in the foreground. Can you also see the mouse, my mouse driver, my mouse pointer?
Yeah.
Okay. We can see some groins for protecting the riverbanks against erosion, but it's not, can't not really be seen here. But I know here is a so-called guiding wall that was built to deflect the current, to guide the current of the river, the flow into the today's Donau Canal. It was important lifeline for the supply of the city with goods, with wood and everything. But we have also a small guiding wall here in the background, and at that time there were already hundreds of such human infrastructures hidden in the floodplain. And the main focus for today is how can we characterize the state of the Danube and its floodplains in hydromorphological terms before the onset of the river regulation. And the other aspect would be how can we reconstruct the natural and man-made changes and make them measurable? Because we do not only want to produce nice images, we also want to extract fluvial metrics data, quantified data that we can use. Yeah, the agenda, Jana kindly already brought this agenda for today, so I can skip the titles of our four presentations, and I can start with the first one on the general methods for spatio-temporal GIS reconstructions of fluvial landscapes. And yeah, the aims for this are to get an overview over the methodological principles for the GIS-based reconstruction of historical river landscapes. Then this shall help to ensure a standardized procedure to generate methodologically comparable data sets for other Danube sections. And this shall also enable analogous reconstructions on other sections of the Danube, so that we follow more or less the same procedure, the same method. Yeah, basic questions, theoretical questions, what for, why we do such reconstructions. There can be different reasons. It can be facilitating the interdisciplinary scientific discourse. It can be impressing stakeholders and sponsors. It's always important to get the money. Gaining public awareness. I have seen that these images we produce are very well accepted in the broader public for exhibitions, for book chapters, even in TV. Then, so the question here arises, which type of graphical representation should be the final output? Should it be an animation, a topographical perspective, a map, or an interactive web tool? Then what kind of information or data shall be highlighted? What is relevant for our purpose? And this goes to the next question, which basic information data do I need for achieving that? Geographical data, land use data, or even socio-economic data? And which historical sources should be used? Written sources, cartographic. We also use archaeological findings and so on. Yeah, the ideal landscape reconstruction should, of course, be able to fulfill all these goals, these aims, to facilitate the interdisciplinary scientific discourse, to impress stakeholders and provoke public awareness, but it should also make fun for the people, for the colleagues who do this job. Yeah, and it shouldn't cost too much unnecessary extra work. So we follow generally a bottom-up approach, which means the same information, data, and methodological work steps should enable both the scientific research and the representation of selected results. This means starting from the historical sources or archaeological findings, we do not directly compile virtual representations of any kind. Instead, we make it stepwise. We first have to interpret the sources critically, making data analysis. Then we have to discuss the results and to interpret it, to draw conclusions. And the final step would be the, let's say, the illustration of the results. Yeah, we called it the regressive iterative GIS reconstruction method since the year 2013. I made this the first time during my dissertation already 10 years before. And there are three main steps. First means georeferencing of scanned maps, starting from the current situation and going backwards in time step by step. This is the regressive approach. Then we vectorize the georeferenced maps, which means we draw polygons, polylines, also starting from the current situation, going back in time, also the regressive approach. And the third would be the revision of the already compiled GIS maps. Here we revise the younger time situations that are closer than to today, based on new information we gained from older time situation, let's say for 200 years ago. So this is the iterative approach, as we will see later. Yeah, the starting point is, as already said, the current situation. It's clear we have the best data. Normally, commonly they are already georeferenced, which means orthophotos. Optimally, we also use the river mileage system. Here you see every 100 meter along the Danube River we have the survey marks that can be easily used for georeferencing maps from the 20th century or aerial images from the 20th century. And we have a problem that because of the vegetation, we often do not see what's below the vegetation. So we use normally also airborne laser scan data with a resolution of 1 meter. This helps really a lot in combination with the orthophotos, but you can also use digital elevation models with, let's say, 5 meters resolution. Maximum would be 10 meter normally. Then it's really a little bit coarse, the digital elevation model. And these are normally our basic data we start with. And then we start with the georeferencing of the first historical data. If we go backward in time, of course, first this would be orthophotos. Okay, orthophotos are already georeferenced, but aerial photographs that are not georeferenced, as you can see here, the Danube flight from 1959 can be easily georeferenced, at least along the riverbanks with this river kilometer system provided by Via Donau in Austria. But in the backcountry, it's more difficult because we do not have so many points like this. Yeah, of course, then you have a great variety of historical maps. We usually start in the 16th century up to the 20th century, and you can see here one of the best maps from 1726. These are in fact, this is a whole map series of numerous maps, and we have to georeference them for constructing our time situation in 1726. Yeah, how can we georeference such maps, historical sources? We use historical landmarks. Here's the situation of Vienna, the river landscape in around 1570. We use important buildings like churches, castle, palaces, important road junctions that are remarkably stable over a long time, over centuries often. We use land property borders, as you can see the brown line here. We use defense structures or important roads, like here the Prater Main Alley that existed from 1539 onwards till today. But very important for us were also bridges, historical bridges, which means bridge remains, archaeological findings of bridge remains. Um, they helped us a lot to locate and to georeference the very old historical sources. And we did this for Vienna. Here you see a map of the bridges and the roads running through the former floodplain in the last 500 years. You see it changed a lot because of the numerous floods, and they had always to renew the road system through the floodplain. And so we had a good, pretty idea of together with archaeological findings, with the maps and so on, where the main river crossings were, and this could helped us to identify correct positions for historical maps. Yeah, here's another example for georeferencing the Bassetti map. I guess some of you will know it because it's a very well-known map. It stretches from the German border down to the end, to the lower end, downstream end of the Iron Gate, from 1857 to 1867. And I had to georeference it 5 years ago by order of the Austrian National Library for an exhibition. And what I want to show here is many only georeference a historical map with 4 reference points, the usual manner. But in this case, like in most cases, then you would have errors in the geographical position of up to 100 or some 100 meters, often depending on the accurateness of the map. And so in this case, we used we used 43 reference points um, to improve the correct position of the map, and we generally use the so-called spline transformation function. This showed for us that it brings the best results. We already had maps with more than 100 reference points per sheet of map. So, but it depends on the power of your computer to calculate this, of course. But many only make georeferencing with 4 points at corner points of the maps, but normally then you have great errors in the middle of the map. Yeah, georeferencing, as we already said, we start with the youngest maps and provisional georeference all maps we intend to use in the project backwards in time. Then in the next step, we accurately georeference the maps that we need for the first historical time state, time situation we will draw in GIS. For the first, we are based on the current geodata. Then we make the GIS map based on the more accurately georeferenced maps. But we do not only draw it according to what we see in the map. Here we check every structure in the map if there might be a still existing possible error of location, of accurateness in the map. So it's always for each structure, for each polyline, for each polygon, we always ask, is what we see in the map, is this logical, or is it rather an error of the survey or something else? Yeah, if we have made this GIS map, then we improve the georeferencing of the formerly provisionally georeferenced maps for the next time situation. And here, as a basis for that, we can use already the GIS map that we produced before under point 3. So it's a stepwise approach. First, we georeference all quick and dirty all maps, and then step by step we can more refine the georeferencing for each time situation. Yeah, and then we start with the next drawing, with the next GIS map of the next older time situation. Yeah, so vectorization or map drawing is also starting from the current situation going backwards in time, the regressive approach like we did for the georeferencing. And the third step is the revision of our maps, of our drawn maps, the revision of the already vectorized younger time maps based on new information we gained from the older time situations. This is the iterative approach. I will show it now. I will show it in the next slides. When compiling such vector maps, it's important to know what shall we draw at all. You see on the left side our typical layer, our GIS layer for such projects. It's quite a lot, but for most important are the landscape features here that refer to different elevation zones of the landscape relative to the water surface, which means water bodies are the blue here, are the deepest landscape feature. Sediment, unvegetated sediment bars are a little bit higher. Low-lying vegetated areas, the light green, as you can see here, these are abandoned vegetated river arms. These are low-lying shore zones, riverbanks, low-lying small islands, and so on. They're a little bit higher already. Then we have the middle green, the main floodplain niveau. This is the general floodplain niveau. And we also draw older and higher river terraces and hills and mountains that may be very close to the river. And we always want to draw these water bodies and sediment bars at low flow situations so that we can see the sediment bars, because this is also of interest for some ecological questions, and also in former times they were often mapped because they were dangerous obstacles for navigation. So they often mapped the sediment bars. Yeah, Then we usually also map different forms of infrastructures in form of polygons like railway stations, cemeteries, large parks, settlement areas. You can see the light gray areas here. Then infrastructure in form of polylines, which are railway lines, main roads, bridges, hydraulic constructions, very important, hydraulic constructions, defense structures, and landmarks, important buildings. This is not really topic of the DANSER project. This is only an add-on, let's say. We do it because we know that the maps are used for other reasons, for museums, for exhibitions, and so on. And so we have an added value doing that. But for DANSER, here, the landscape features are really relevant. And yeah, and you see here a part of the situation from 2023 in our demo site Upper Danube, the so-called Lubau floodplain. It's inside of the city of Vienna at the eastern border. And when this is already finished, and so we started with the revision of so we usually copy the data, the GIS data, in this case from 2023, rename it for 1994, and then we change, modify all river structures that have changed. This here, the yellow lines show the changes that have to be done. In fact, there are even more. I was not able to finish it until now here in this area. But this is only, let's say, a fifth of our study area. So you can imagine this is quite a lot of work. And so we always copy the data, rename it for the new time situation, and then we change what has to be changed. Yeah, so the workflow, as already said, we start with the current situation step by step backwards in time. Let's say here 2010, then 1849. In fact, at that former project, we had several other time situations in between, but okay. Then we go back in time and we copy all structures to 1849, rename it, adapt everything. Then the next step, as already said, we have more time slices in between. Yeah. And as already said, when one time situation is ready, we improve the georeferencing of the historical maps that we need for the next time situation, because then it's easier to make the georeferencing more accurate. Yeah, this is the regressive approach, but now the iterative revision forwards in time. So we see we made let's say 1726 for this is the Vienna floodplain. And then maybe we see in 1726, there are some river structures, water bodies depicted in the historical maps that were not depicted or not shown in 1849, but somehow they must have been visible, still partly existed in 1849, maybe in form of an abandoned arm and of an or already vegetated terrain depression or something like this. Because not all maps always show all details. And so we go back iteratively and add information that might missing in the younger time situation. Of course, we have to adapt it. For example, if an oxbow lake in 1726 normally is terrestrialized. In 1849, one would expect that naturally there would be a kind of terrain depression or something like this. Expect human already changed it. Yeah, and when this iterative process is finished, then we do the next former time situation. And here we see, okay, okay, the river arm here there was a river arm, and in 1726 for them this was not interested any longer, but somehow there must be some relic in the fragment, a fragment of this in the river landscape, because we know how long it takes that certain riverine structures vanish because of the terrestrialization of sedimentation and so on. And or maybe in 1726 we had some structures in the maps we could not interpret. We did not know what they mean. So, and with the information of 63, we have a better knowledge, and we can know better to interpret maybe structures here. So we once more iteratively revise 1726 and maybe also 1849. And if this loop is done, then we do the next older time situation. Yeah, here is the animation for the river landscape in Vienna. And you can imagine to produce then such animations. This is for the new Wien Museum in Vienna. You have to work consistently, which means what remains stable in the landscape should be not changed in the data set. What changes naturally or because of human interventions has to be changed in the data set. So that you can produce a coherent chronological map series. Yeah, as already said, we did this for whole of Vienna for the museum, and this was my own, let's say, hobby work. I produced a WebGIS app. You can see here the link to the WebGIS app. You can have a look on all time situations to zoom in, to compare it with the current fabric of the city. There are 2,600 historical hydraulic constructions here. The orange lines refer to those only for the 19th century. You can click on it and see all the attributes. When was it built? Who built it? What's the purpose? And so on. And yeah, and we first time we published this in a special issue of the journal Water History in 2013. It's open access, and in this special issue there are two articles on that topic, one for the methods and one for the results in context of the history of Vienna. Yeah, and what's next? The next part would be the presentation on the historical sources suitable for river landscape reconstruction. But I will stop here now, and maybe you have some questions, and I will try to answer these questions best.
Thank you very much, Severin. I see there is one question in the chat. I can read it to you. So Sayed Abdu asked if polygon data is already available for 2023 and 1849, why not simply calculate the difference between the geometries instead of digitalizing everything again?
You mean if they are all, for example, if somebody has already a data set for two time situations, and why not to use this, and why to produce a new data set? Is this the question, if I understand right? One problem is always that we have to work coherently. And if you have, for example, if you have have already a data set from, let's say, other projects, then I've never seen data sets that are really so coherently made that they really meet the demands you need. And because of if the question was why there is why should we produce time situations between two already existing data sets, because there are so many, if in a dynamic river landscape there's so many changes, then you would miss several stages in the development of the river, in the fluid dynamics in the river history. And then I will show it in one of the next presentations. Then you will not understand if the time period between the time situations is too long, you miss important information on fluid dynamics and have, like, let's say, a black box. In particular, if you focus on fluid dynamics and erosion and deposition processes.
Yeah, it's not that simple as just, for example, other land covers like forest, where we had forest and where we don't have any more forest. If we had river here and river here, this doesn't mean that the river moved from here to here. It did some very dynamic changes. Yeah.
It can be that it moved, migrated, the river shifted, but it can also jump. This is the case in the so-called evulsion process. So, and if the time between is too long, yeah, then you can't do the work I will present in the last presentation with the erosion deposition.
Okay, great. I hope we answered this question. Any more questions?
Feel free. If the questions come later, you can also ask me.
Sayed, please.
Yeah, one last question. Do you digitize every time on the map which you have by hand, or you use kind of classification to automatically detect the riverbed?
Yeah. This is a very old question, and we finally always came up to really each line, each polygon is checked manually and made manually in order to work consistently. All other methods led to fuzzy data, to problems in the automatic classification. We tried some tools to automatically at least digitize cadastre maps, but cadastre maps, as I will show you in the next presentation, have their own problems inherent. So what I encountered is that only by manually doing this, okay, I do not do it not alone. I have also master students working with me. Only working, let's say, through the whole landscape, I get the knowledge how the river behaves, what the river behavior, how it reacts to human interventions. So it's also a learning process. It's not only for drawing. You learn a lot about reaction time of a river to human interventions, also only because of going so deep into the data and think about every structure you draw.
Thank you. Herman, did you have a question?
Yeah, well, my question was intending to go into the same direction as before. So, because I mean, I know how cumbersome it is to digitize maps from the past. So there are a lot of tools to, as you said, who might overcome this very lengthy process of digitizing maps. I mean, like object-based image analysis, you can define rule sets and define exactly what to consider for the map to be digitized or not. And then you can sort of classify that in a way that it is reproducible. And that is something which is quite important to science that you can redo one and the same study again and again with the same results. And this would offer the opportunity. If there are some mistakes in there, the mistakes are in the rule set, you can sort of change the rule set in classifying related maps. So that's
this would be interesting to compare it. Let's say, manually with the rule set base. This would be interesting. I've seen the different sources we need, we use. They are so different in quality. Each map, the symbology, the map distortions, then you will see in the next presentation, we do not only use maps, we use many other types of data. But it would be interesting to compare it, the results.
Yeah, maybe one further comment to that. I mean, since now artificial intelligence or AI is becoming more and more important, I'm not that much into image analysis things and the AI, but I wonder whether there are also opportunities for systems to learn about those types of distortions in maps and to self sort of automatically correct those things. But this is maybe something which we could look into in the future.
Definitely. This is interesting. I honestly have to say I have no experience in that, and for me, it's already said, it's also for me and for my students, it was also a learning process. If you really have to think over each structure, is it an error in the map, in the survey, something? And so you learn a lot. So it's also a other thing to have a look on this procedure.
Okay, super. I also find this topic very interesting, especially with our Department of Geoinformatics. But now we need to move forward for the next presentation.
Okay.
And I hope there is then time after that for more discussion.
So I have a look for the second presentation here and here, and data sources. So I hope it works.
Yes.
Okay, Okay, now let's go to the data sources we usually use. Here are topics: what types of historical sources are generally available, what are the advantages and disadvantages of different map bases, and what information can be obtained from cartographic sources with regard to the hydromorphological characteristics of a river. And basic question. In an ideal world, the primary question would be which states of a river landscapes or which point in time should be reconstructed and investigated. So usually we do it for several time situations prior to regulation in order to capture the natural fluid dynamics. You need several time points in time to see how a river naturally changes. Then also would be of interest situation just before the onset of the systematic river channelization, or at the completion of certain regulations, working steps like the so-called mean flow regulation that was first done at our rivers, or the low flow regulation around the year 1900, or flood protection. Then interesting could be also directly after termination of a whole regulation program, then just before and or after the construction of a hydropower plant, and just before the onset of renaturation measures in kind as a pre-monitoring, or other situation would be of interest, for example, after termination of restoration measures in kind of a post-monitoring. And for the DANSER project here in the Upper Danube demo site Nationalpark Donauauen, we capture the natural fluvial dynamics by around 1726, 1780, 1820. Then just before the onset of the systematic channelization around 1875, directly after the regulation program in 1915, and then directly when the hydropower plant in Vienna was built in 1994, which is the same time just before the first renaturation measure. Yeah, and the today's situation. So this would be ideal, and we have the chance because in Vienna we have so many historical sources and data. This is really very helpful. But in the real world, the primary question is more, do we have sufficient historical sources to capture the past? This means we have to review. A review has to be done of which historical sources are available for the optimally selected time situations. Then we see, there are some lacks in historical data. We unfortunately maybe have to change the selection of the historical time situations based on the available sources. And then an additional archive research is necessary for the ultimately selected time situations to find potential additional archive material, maps, and plans. Yeah, types of basic data. Of course, typically historical sources. We also used written sources. Of course, cartographic are the most important ones. Then historical, topographical literature, current literature, technical reports, hydrographic data. Then we use, as already said, archaeological findings. Here is a riverbank protection from the first in the center of the first district of Vienna, where nobody would think about that there was a Danube arm once. Then, of course, geological and soil maps are very helpful. Then the flood histories of interest, because they are very strongly interlinked with the fluvial dynamics. And very helpful, of course, is the knowledge about typical geomorphological forms and processes of the specific river type. This is, in my case, I have good luck because this is my profession. Yeah. Then what is needed for the features, for the map features we want to draw, to extract? You see on the left side once more what we have already seen, the layers in the GIS, and you have seen that the landscape features are that of most interest for DANSER. And as already said, water bodies most interested would be of highest value at low flow situation, but minimum requirement would be that they are mapped at the mean or summer mean flow, and sediment bars optimally also at low flow, because at higher flow or at summer mean flow they are largely submerged, and you can't see them in the maps. And what does summer mean flow mean? This is the mean water level during vegetation period. This refers approximately to the so-called active channel. And the active channel is the water surfaces and the unvegetated sediment bars. That's why you see it here in the map. It's the the border of the lateral limits of the active channel is the vegetation border of the woody vegetation, as you can see here. And this can be seen in most historical maps and also in orthophotos. And because we always have the trouble that the water level of survey in each map is not the same and differs. And if you calculate then water surface areas, also or sediment bar areas, they always depend on the water level of survey. And this if you focus on the active channel, this can be seen in the maps, in the photos, and it's clearly defined. And at the Austrian Danube, and I think at longer Danube sections, it's the summer mean flow as the flow during the vegetation period. Yeah, then the low-lying vegetated areas, as already said, these are vegetated areas along the riverbanks, low-lying vegetated islands, abandoned river arms that are already vegetated, must not be analyzed, but are very helpful because they show us the location of former river arms in the floodplain. And then it's easier to georeference historical maps because you see, okay, the terrain depression, the vegetated trench in the floodplain, this was the active river channel in 1849, for example. Yeah, the main floodplain niveau is more or less the remainder of the floodplain, so all area that is not water, not sediment, not low-lying vegetated terrain, which means this must not be drawn separately. This can be clipped out of the rest by the other polygons. And all the higher river terraces and hills, mountains are not necessary, only for better illustration. And as already said, the different types of infrastructures are all nice to have. If, for example, we do a lot of environmental historical studies. Here, for example, the settlement history is of interest, the expansion of settlements into the floodplain, the history of infrastructure is of interest. So, and as already said, it makes the reconstructions more, let's say, more interesting for other purposes, like for exhibitions or so. Yeah, and now I go through the different historical sources we use. I start in the 16th century, where we normally only have written sources, some small maps or plans in the 16th, 17th century, and I speak for the Austrian Danube, but I think it's similar to other Danube sections. Before 1560, we have only mostly written sources about the local river status, often reports on flood damages or technical things about hydraulic constructions. And after 1560 up to 1680s, we have first maps for river engineering measures, as you can see here. This is upstream of inside of Vienna, the northern part. Local river engineering measures, some military maps, some topographical views. So the content here is very diverse, and the problems are manifold to use them. We have a lack of details, lack of consistent scales, errors in geographical positions, and we can use them mostly only by using the regressive iterative reconstruction method if you go step by step backwards in time. Otherwise, if you would want to georeference this in the current river landscape, you will have no idea where to put it. Yeah. Then in the late 17th to 18th centuries, we have already better maps, plans, and topographical views. From the 1680s to 1770, we have first maps of longer river sections, military maps, river regulation plans. Here's a very wonderful map from Anguissula's 1688, the river landscape close to Vienna. You see here the city of Vienna. It's a very good example. It already shows it's a plan for river regulation. And in the early 18th century, we find a new genre of sources, topographical views and city maps that were sold for commercial purposes, for tourists, let's say, already. The content here is also very diverse. We have manifold problems, but less than in the 16th century, with a potential lack of details, lack of consistent scale, potential errors in geographical positions. And these sources can be also only mostly be used when we used the regressive iterative reconstruction method, because otherwise it's difficult to find enough reference points where we can fix the maps in the landscape. Yeah, and then there's the time of the military surveys that cover the whole Habsburg Empire. These are the first systematically surveyed large-scale maps. There are 3 of them. The first military survey from the 1770s to the 1780s. It's unfortunately very inaccurate, only accurate in or close to larger cities, have a lack of detail, great errors in position, inconsistent survey. So it's in some areas, you hardly can't use it. The second military survey from 1809 to 1869 is much better than in the first military survey. It shows more details, but also some position errors outside larger cities are evident. And the third military survey, starting in 1869 to 1887, this is really a good source, mostly very accurate, many types of information, landscape features, hydraulic structures. They even distinguish often between wooden bank protections and bank protections made of stone and so on. And here the content is topography, which is important in floodplains, for terrain depressions, for trenches, for abandoned river arms, water bodies, land cover, infrastructure. Yeah, the problems, as already said, are different for the first and the second military survey. The first military surveys can only be used also within the regressive iterative reconstruction method. The second might be sufficient for large-scale studies along longer Danube sections. Yeah, and then comes the time of the more systematically surveyed river maps and navigation maps of longer Danube sections, starting around 1800 to the early 20th century. Here is the well-known Bassetti map, made in Vienna 1857. Of course, they are focused on the river. They shows diverse fluvial structures, often with sediment bars. We have here a lot of sediment bars indicated here. Then hydraulic construction. Okay, it's clear it's the purpose of such maps, a lot of hydraulic constructions. Hydraulic data like water depths, in this case also flow velocities, and so on. The problem is such maps focus on the river and accordingly have potential lacks of details in remote areas of the floodplain. But they also have potential errors in geographical position. In particular, in Austria, the Bassetti maps is awful. It's very interesting what is shown, had a great value, but it's awful for georeferencing. Usage, best choice. It's a good choice for reconstructing water bodies, but lack sometimes water bodies in the floodplain. And yeah, the Bassetti map, very well known, as already, I guess I have already said, I georeferenced it for the National Library in 2020. And in fact, there are two types of the Bassetti map, the so-called Schifffahrtskarte der Donau 1857. This was the first map series. It was also made in color, but the geographical position is awful. And what is known as Bassetti map is later from 1862 to 1867 downstream to the end of the Iron Gate. And yeah, I georeferenced it. Here is a detail from the Danube at the entrance of the Iron Gate at Golubac or Golubat. Sorry, I do not know how to pronounce it correctly. And as you can see here, it fits quite good. Of course, I also used here, I guess, 25 reference points to adjust it. But for Hungary and further downstream, it's quite good surveyed and provides a lot of information. Yeah, and very informative and helpful are cadastre maps and detailed river survey maps from the first half of the 19th century. In the former Habsburg Empire, we have good luck. We have the Franciscan cadastre, which is, in many other countries in Europe, they do not have such cadastre maps from that time. And they are very accurate in position. They show each land property parcel and the land use or the land cover. But they are often, or the most time, lack of fluvial structures, no sediment bars, no hydraulic constructions. Here in the detail from Vienna, it's better because in Vienna all maps were made better than outside of Vienna at that time. Here they have sediment bars, this area, and also hydraulic constructions, but in many areas of the former monarchy there is no such information. And you also do not have really terrain topography. Of course, you see this here, this is an abandoned river arm, but you have no idea about the topography in the floodplain area else. And so good luck at that, more or less at the same time, the first very detailed river survey maps were made. Here for Austria around 1817, it shows the same area compared to the cadastre. Here we have all types, sediment bar, water depths, hydraulic constructions, and so on and so on. But they sometimes have incorrect geographical position. In Hungary, or what was formerly Hungary, there is an incredible good data set from the 1820s and 1830s, by much better than in Austria. Very detailed. It's incredible that could be used for such studies. The whole floodplain was mapped at that time. The cartography, the fluvial cartography in Hungary was at that time much better than in Austria. And yeah, and so the best procedure would be to combine both. You have the geographical position, you have the structures, and to combine both for your reconstructions, to overlay it and use both information. Yeah, and then in the 20th century, we have a lot of topographical maps, mostly in the scale 1 to 50,000 or something like this. Here you see on the left side the Austrian typical topographical map from 2020, on the right side from 1960. And of course, they show the topography, water bodies, infrastructure, larger hydraulic constructions. But problems are older maps, not only in Austria, also in Hungary, as I see, show position areas. And what's clear, also in the younger maps, landscape features are generalized, which means that streets are broader, water bodies show a larger width of often it's generalized and not so detailed. Yeah, but it can be used for larger water bodies. The larger the water body is, the more okay is it, and it can all, of course, used for large scale studies, of course. Yeah, and my last, no, not almost last one, are the river survey maps and navigation maps from the 1930s onwards. These are really often good maps. Here is an example from Hungary. It's a perfect river map showing a lot of detail. There's a whole series of maps from the 1930s in Hungary. Really a good example. They show detailed water bodies, in-stream structures, infrastructures, hydraulic construction, water depth, partially also the floodplain topography, as you can see here in the floodplain, the topography shown here in form of ridges and depressions in the floodplain. Yeah, really high suitable for detailed landscape reconstructions. Yeah, and finally, we have already talked about this, the orthophotos, already georeferenced, or aerial photograph, not georeferenced. They are, of course, very helpful, but show all features needed for reconstructions, but the sediment bars depend on the water level of survey, and overhanging vegetation can hide geomorphic features on the ground so that you can't see it. So the shading of the vegetation might be a problem. Yeah, that's my from this side. Yeah, if there are any questions, then now. Otherwise, we have a coffee break for 10 minutes, and then it's on Ulrich Schwarz's his next presentation. Examples for the entire Danube steps towards fluvial homogeneous reach definition. So many thanks.
Okay, super. So if there are no questions, or if there are questions, of course, we can do them also after next presentation. Let's say we're starting now the coffee break, and we will be back at 2:18. Yeah.
Yeah. Okay, yeah.
Okay, super. See you in 10 minutes.
Thank you.
See you.
Hi, 1 more minute to go.
Yes. So, Nikolova, I think it is possible to share the screen already. Yeah, I think so.
It should be, yeah.
Should be, yeah.
Uli, if it doesn't work to share the presentation, let me know. And
we can test, or I can already start it.
Super. Okay. I hope everybody is now enjoying a cup of coffee and are refreshed after this short break. I see Severin has his. Okay, and yeah, I think we can start now with the second part of the workshop.
Okay. Yeah, welcome everybody. Maybe just seeing some additional faces. So my part will be to give you to show you examples for the Danube, for the entire Danube, but also for upper, middle, and lower Danube. Basically, I have to say from my side, from Fluvius, so we are working almost 30 years, like Severin, but of course on a more broader reach of science and applied projects in the field of hydromorphology and floodplain ecology. But historical maps in particular and analysis are of greatest interest. So on the top view, you can see here already the Siget curse and a quite nice visualization. I also want to start giving you some impressions of historical maps. Thanks to the excellent presentation of Severin, we got already a nice overview on the basic situation on maps, which features can be extracted from the maps. Maybe in this start screen here, you can see on the left upper part the Lech confluence. Yeah, maybe it's possible to see also my mouse. So the Lech is a mountainous river, even braided river, joining the small Danube coming from Black Forest merging together to a new river system. Yeah, and a new river and floodplain system in size and magnitude of flooding and so on. Very beautiful map from the middle of or early of 19th century. Then you see the Efferdinger Becken. This is quite interesting or fascinating, in my opinion, in particular, as it is first basin downstream of the Inn confluence. The Inn is the biggest tributary of the Danube, very rich in sediment. And this Efferdinger Becken, upstream of Linz, is, let's say, somehow the first compartment of floodplain situation in the river Danube, where most of the sediment, coarse sediment, gravel mainly, is deposited. And this is from the first survey, military survey in Austria. Of course, Severin explained all the strong limitations. However, you can imagine that this kind of river type and plan form is really unique for the main river Danube, not for some tributaries, not for the mountains, for the high mountain reaches, but for the Danube, this is unique. Then we get left bottom some view of this so-called Parsetti map near Rijeka, near the Slovak-Hungarian, so from the middle course of the Danube. And on the right side, we see the Tisa confluence in Serbia, where we get really in this Bačka Vojvodina area, very beautiful, interesting features, morphological features. I call them truncated meanders. It's quite nice. These are meanders which cannot be developed at all. The river tries to build meanders, but always the steep, less cliff or high bank is preventing the shifting southwards. And we have this beautiful, nice lens of less, which is very hard material and up to 100 meter above the valley floor, and the Tisa is coming here from north, from Hungary, and even this less structure was flown. The water was flown around, so it's fascinating. Again, near Novi Sad or Peterwardein, 2 shots further of the Parsetti map, which already also Severin shown. We have this extremely interesting exorbitant lateral development of the river. Later on, this was all totally irrigated and is not existing anymore. We see the Eisernes Tor, the Iron Gate, in its original in the original situation in the Parsetti map, a very spectacular cataract system of the Danube. With only a very few navigable routes through. Later, the Germans in the Second World War built a railway pulling up the rivers, the ships, the barges from downstream to upstream. And also even looking for the lower Danube. So we have the big map here is also coming from this 18th century. And we have really very significant and important floodplain features. I will show you this later a bit more, on islands in the rivers, of wetlands, of very shallow floodplain lakes, which are very typical, and tributary confluences. But also the Danube Delta is a long subject of historical analysis. Julian, you will for sure show us beautiful, nice examinations and elaborations how the Delta developed. And simply these are some historical navigation maps, so you can see also the shipping depths here, and the Sulina branch Tulča is here, and you can see that this the Sulja branch was not built at all, of course, at this time. Let's look for what I want to talk about. I will give you examples, and I will not only show you historical maps. I try to show you applicable applications, or already also results of those historical analysis for entire Danube, but also, of course, for upper, middle, and lower Danube. I will give you only on one. I will do it not too theoretically, but on 2 slides, talking about the subdivision of morphological homogeneous sections. I bridge it or link it also to the Joint Danube survey, because I will show you later in the Danube for All project. Very recently, we had workshops, and we are in preparing this segmentation, let's say, sections for the Danube River Basin, even with tributaries. And finally, I give some ideas for potential reaches, which are maybe of special importance and fascination also, I would say, to map on Middle and Lower Danube. And finally, of course, they have all significant influences on the sediment balance, sediment household, erosion. However, on the start screen, I show you some pictures from Vjosa River in Albania, because we done this very recently. Simply, I want to show, we talk about historical maps and historical situations, but of course, also as this segmentation, classification, remote sensing techniques were mentioned. When we have satellite images, it is possible. The case of Vjosa, we have for the last 20 years so much dynamic that in this colorized main channels or channels, you simply see all channels of the last 20 years. So it is incredible. So what Severin prepared for Vienna for the last 2000 years is possible to prepare for the Vjosa, which is a totally different braided river system in the mountains in Albania, much smaller river. But you can see what you see in 2000 years, you can here show in 20 years. I simply want to put this as a kind of appetizer or something. So we have only one older scene. It's from 1968. It's a corona image from the US Intelligence Service. So let's talk about historical mapping examples for entire Danube. We start also with the Auen Institute, Floodplain Institute in Rastatt, 1999, on a study of Danube pollution reduction program, a so-called wetland study. And we use the general map, Generalkarte. This is a very general 1 to 200,000 scale map of the Danube Basin to delineate the floodplain. This is, of course, one of the main applications for many projects to derive the active and the morphological floodplain. The EU project on Danube flood risk in 2012, but even more the project on Danube floodplain 2020 use historical map data also for characterization of floodplain. I simply put here one spot. There is a so-called FFEM, floodplain evaluation matrix. It is simply quite interesting that they also explore hydrology, hydraulics, ecology, socio-economy. So you can imagine or understand how important it is to know what we found in the floodplain. So what is the current situation and what we had in the past, because this floodplain evaluation matrix significantly helped to discuss issues like peak flow reduction, water level change in duration of flood, and so on. But you see also connectivity of floodplain water bodies is some indicator. Unfortunately, sediment, the topic of sediment was neglected for the Danube floodplain project, which is a little bit a shame, I would even say. But on the other hand, they try also to collect a lot of information about floodplains. The third issue regarding the entire Danube, and now we are coming much more back to historical data and information, was the Danube Sediment 1 project. You know that actually we have the second phase of this pure Danube sediment project, And so we mapped the entire Danube. Yeah, however, for instance, for the Hungarian part, we used, or not we, but the Hungarians, for instance, used the second survey. But in the second survey of about 1850, of course, we have many meander cut-offs. So it is quite a good situation, quite a good base, but it is maybe not the real situation which is here the idea behind, because it's a kind of reference situation. So the Sediment 1 project, we have a huge project report on the historical development. But what you can see here and what is obvious in the right side corner is a clear length development of rivers, strong rectifications. And here in the bottom graph, you see in yellow, you see islands and water in blue. This is so quite impressive also to see how the Danube is really reaching 10 kilometer in width here in the southern part of Hungary, and of course in the delta much more. That's for examples for the entire Danube. Now I'm coming to the upper Danube and split into Bavaria, and one slide for Bavaria and one slide for Austria. So in Bavaria, there's one quite nice work of Skublic and Rutschmann from 2016, trying to extract the digital terrain model from the historical maps and seamlessly. That means really for a Danube reach over 30 kilometers, approximately 30, 40, even more. And what you can see here is that when you run a rather simple 1D flood model or something over this current elevation model and the historical elevation model, you can significantly see differences, and you can also, of course, estimate what that means regarding sediment transport, accumulation, remobilization of sediments from the floodplain, and so on. So this is, of course, that would be really a great feature, or is a very great feature, when we are able to reconstruct by historical data, even the historical terrain models, to do modeling. For Austria, I'm very quick and fast. You know the excellent work of Severin and his team. We got really the first systematic stepwise regressive historical analysis of a river, I think even in Central Europe. Correct me, Severin, if I'm wrong. It is very important how important it is to map iterative and many time steps, not only one time step, because it is very important to understand the development and behavior of the river landscape. And here, if you compare the spatial temporal development, you get a clear time developments. You can see this starts in early 18th century and ends in the post channel in 1991. So you can see what happened. We have here these different kinds of connectivity of riverine water bodies. For instance, this Eupotamon means that side channels are connected upstream, downstream. Eupotamon B, when they are only connected downstream. Parapotamon are then oxbows, and so on, or not oxbows, but temporarily connected side channels, and so on. So, and this is quite very important. The second issue is the so-called rejuvenation and the age of habitats. So this is very important. also, if we want to determine the age and development of oxbows, for instance, this is maybe known for a much longer time also in science history, but rejuvenation of the most dynamic parts of the river, namely the all kinds of gravel and sandbars, but also pioneer stands and the biogeomorphological phase, meaning with willow and poplar shrubs. And then finally, of course, with young, low-laying softwoods and hardwoods. This is quite fascinating and very impressive to prove it, yeah, to map it and to prove it how this is developing. So you get vectors of particular habitats and they develop in one direction. So finally, what does it mean in this highly altered or really heavily modified river landscape in Austria or in Germany? See even total loss of habitats. And finally, if you look at the age of habitats today, yeah, the forests in these pockets, in these floodplains, are over 150 years, 160 years clear, because they are not changing anymore. Yeah, we have riprap on the river, we have hydropower regulation, we have the big flood dikes, and everything is changed. While in the past, yeah, the habitats shift between 30, 40, 50 years. Yeah, and this is really a stunning and very important knowledge that we gain here by Severin's work for Austria. But we have also a lot of colleagues coming from historical science, from geography, dealing over centuries with the development of landscapes and also rivers. One of these guys is Peter Pischut in Bratislava, for instance. Here it is quite interesting. I already mentioned this part downstream of Vienna and Bratislava, where we have this, I would call it inland delta, but it is not a delta. It is a transition phase where the river loses a lot of gradient, yeah, of slope. And in this part, there are huge accumulations of coarser material and also already fine material. And the river spreads out, and we have here in this Siggetkurs and Schüttinsel even 3 stems of the river, the northern part in Slovakia, the middle one, which builds the border, and the southern one, the Muzhony Duna, which builds the southern one. And it is quite interesting, and this is in particular for the city reach of Bratislava, quite interesting, the importance of ice floods, yeah? And also, of course, of the small ice age in the 19th century, but even also earlier. So this is very important, even to synthesize or get an idea about the flood behavior and flood history of our landscapes and large rivers. And they can influence if you get here 2 or 3 side channels and how big they are, which river type and plant form they have, and so on. So this is a very important issue. Then let's talk shortly about the Siggetkurs. And you simply see here, I done in 28 a work for the Hungarian Environment Ministry. It was about the restoration of Siggetkurs and different scenarios. But simply to show what also Severin already mentioned, it is very important to collect systematically the historical sources. I mean, I really focused here on maps, but Severin is fully right. We have much more information than only maps, and I know Severin dedicated his life to explore and dig out a lot of very useful and helpful information. So I try simply here to get some ideas if this is important for land use, habitats, hydromorphology, river engineering, and how these topological issues can be used. So this is a simple, simply also showing some of the major steps, and maybe in difference to what Severin showed. So we also try. In this case, we really try also to map this eupotamon, parapotamon, the connectivity of the system. And simply, if you look here at 1910, you see that all these dark river branches here, and all this was really cut off by river regulation, by really a strong bank, guiding walls, closures of side channels by cross dikes, or by fascines, by wooden structures, doesn't matter. But so I simply want to show that there's a clear shift. And this system isn't particularly interesting because it was first of all even more not meandering, but ana-branching instead of building so much branches. And you can, if you analyze maps in this way, you can give some basic estimations of the history of regulation. Regarding mean water regulation and low water regulation, and of course the construction of Gabčíkovo finally. This is a big, huge hydropower plant. And you can see here a clear decline in side channel connections per 5 kilometers. The sinuosity is decreasing. You can see the length of shoreline main channel is decreasing. Average island perimeter in meter is strongly decreasing. The maximum width main channel is changing. Minimum width channel is, so it's a homogenization of the channel, of course. So it's very helpful. Going a little bit more further down the Danube, we talk about the Mura-Drava Danube river system. So we done mappings on the historical situation and on training structures. It is absolutely obvious if you look at those pictures here that so you can simply not recognize the former river landscape. So we got also strong losses in main channel, side channel, sand and gravel bars. It's up to, and look at the island loss, for Mura, minus 96%, So for Drava and Danube, it is better, still better. So again, some pairs of comparison, but again, I have to say, of course, in many projects, you have not the budget and working space to analyze a long time series of maps, to analyze 5 or 10 historical maps. And that was here also the case. Therefore, the historical situation was, and that's another, let's say, challenge to bring those maps together into one comparable fit. And you simply can see here the Mura on the left side, the Drava in this hydropower section, and the Danube just downstream of the Drava confluence. You see here one of the most fascinating, interesting floodplain part of the Danube, which is totally destroyed today or removed, simply removed by agriculture. Then I'm still keeping this middle part of the Danube. I know that we have also Croatian colleagues among us. Therefore, maybe the Hungarian part is not so interesting. But I think for Danube, for Drava and Danube, it is, of course, very important and significant. In my PhD, I done some analysis regarding the reconstruction of the development of meanders and also the so-called, and here we already talk a little bit about the sectioning of the river. So, and you can see that river was really purely meandering with a very, very high sinuosity. Same also for the Drava, for the lower Drava. And if you have not enough and systematic historical maps, in front of you. It is also, of course, possible by this typical ribble and swale landscape relief of the floodplains to reconstruct channels and meanders quite easily. Yeah. So you can also reconstruct intermediate stages. Yeah. So it is really the case that you need not for all the maps, for all decades, let's say, or 20-year steps maps. It is also possible to reconstruct it. So this is, of course, one of the absolute hotspots in floodplain and river development till today, I have to say, for Middle Danube. And another example for Lower Drava, it's also not a new example, it's coming from 2013. On Lower Drava, we have a kind of river history, which is, in my opinion, and I know Europe really quite good, which is really unique, because we have here Osijek. It's close to the confluence into the Danube. So it's really the Lower Drava. It has 550 cubic meter per second mean water. So it is a huge river. And under the Austrian-Hungarian monarchy, this river was completely rectified. I also overlaid here some structures I got also from other maps for navigation. Yeah, the Austrians and Hungarians, they like to go by ship to I don't know, to barge and even more upstream. So there was a Donaudampfschifffahrtsgesellschaft, a huge shipping company from Vienna, and they tried to go everywhere by big ships. But this rectification was not really, let's say, successful, but long-lasting. And after the monarchy, the river start to re-meander. Yeah, so by themselves. So no restoration work was done or anything like this. This is a pure natural power to re-meander. And you can see now finally here 1997. So we are 25 years later, and in the last decades or 15 years again, we get some river regulation, we get a highway bridge crossing. So there are some more deteriorations again. Yeah, but until 1997, the river really start to re-meander. So this is a very impressive example, in my opinion, also nicely showing this in the historical sequence. So, and now at the end, talking maybe about what is more technical. When we talk about the subdivision of morphologically homogeneous sections, this is very closely connected to hydromorphological standards, yeah, to methodologies, how to assess hydromorphology. And I will also, let's say, bring it in line or shortly discuss it with the GDS, you know, the Joint Danube Survey. The first was started in 2021, and all 6 years the Danube was assessed going by ship, the entire 2,400 kilometers from Kelheim to Sulina. And in the first years in they used 24 and 2010 as Seine. This Seine is quite interesting. This Seine is pressure-based. Yeah, pressure-based means you have a kind of reference conditions, which is of course also derived or recognized by historical maps and information. And if you look for the pressure, for instance, of bank revetment, bank reinforcement, riprap, but also groins, guiding walls, etc., etc. If you look, you can assess, you get the stretch or assessment reach, and you can say 50% of the banks are modified. Yeah, they are with riprap, they are stabilized, the river cannot shift anymore laterally. So this is the original old Seine standard. You see here also a small map That was carried out until the last years, the 20s, because with the 20s and 24, the new standards fully recognized also the reform, so-called reform project, EU project, which is really a project based on processes, on the fluvial processes, on the hydromorphological dynamics, the interaction of erosion, accumulation, and building processes. So it is much more demanding, in comparison to the pure pressure-based approaches used earlier. But of course, they will give a much more concise and better understanding also regarding the scaling. So we really can start on the catchment and landscape unit. We have so-called river segments, we have river reaches, and very small units which are not from interest for us for the Danube. But the river reaches are important. They are also a little bit controversial discussed when we talk about the Danube. Maybe the 10 kilometer, it's a huge river, and this system was elaborated for all rivers, of all larger rivers. But I have to say that we should really look maybe to 10 to 30 kilometer segments. It is, of course, obvious and very important also for our project. I mean, the DANSER project is dealing exactly with what we see here, with the catchment, the water input, everything, hydrology, what is coming into the rivers, and the sediment input is, of course, crucial. And on this reach level, we get, let's say, those conditions, base conditions, together with anthropogenic activities, river engineering, sediment management, flow alterations, etc. And we get a kind of river response on this reach, but even not on the reach, even on the segments. So this is something, so I grab this from the approaches of GDS5. These are Boku graphics, also from the other Danube for All project, I guess, or Danube Sediment Plus. But so this is a little bit tricky. Of course, this input is not only on river reaches, 1 to 10 kilometers. They are, of course, here on this major segments, on the big, huge reaches. So if you have the Iron Gate, the problem with the trapping of sediment is causing problems hundreds of kilometers downstream, not only 10 kilometers on the river reach. So therefore, this graphic is not perfect in my opinion here. But in generally, this is exactly how we should discuss it. And so the final slide then is going, or now it's the second, not the final, but the second last, is how to start such a definition of morphological homogeneous stretches. And here we have core parameters. There are even more, but you can see, I told you, this new approach of hydromorphological assessments and the new standards are very demanding, in my opinion. What we can rather easily get out from maps is the valley confinement. So if there are terraces, if the river is going like in the Iron Gate or Wachau through mountains, and then the plan forms, namely here the number of channels, so single thread, then the plan form type, that means if it is sinuous or braided or anabranching. Then it is very important to look at the hydrological impact or stretches. If they are major tributaries like Drava, Sava, Tisa, we have most probably boundaries of these homogeneous sections. Then which is also easily available, is a valley gradient, or not so easily available if you have a very low gradient, of course. Yeah, but the valley gradient is very important. Then bedside sediment grain size material is very important, and of course, let's say the major anthropogenic impacts, mainly by major dams and barriers. On the left side, you see here the Danube GDS2. It's a very old slide, so that we also use the Passetti map for fields. These are fact sheets used in the field. But finally, what we should use, and this is, let's say, the latest version of the segmentation. We just finished a workshop on it. And most probably it is helpful, at least also for us, to find appropriate places. And this is my last slide. I simply point to some potential reaches on the middle and lower Danube. We know we have no partners, I guess, from Hungary, from Serbia. Therefore, many of the or Slovakia, they are mainly in the other projects. So we have definitively the Croatian colleagues here. So I would be very, very interested to having here these two stretches from the border, Hungarian border to Erdut, and from Erdut to Ilok, Vukovar, Ilok. And then, of course, in Serbia, so we have no Serbia, therefore it is not really interesting. For lower Danube, it is, of course, the island sections. So if you look at the 800 or 600 kilometer of this border Danube between Romania and Bulgaria, so you have different island sections. Yeah, these are not accumulations of islands, but in the gradient, it's quite interesting. So, and of course, it would be very important to take out such an island section. Then further, the tributary confluences are, as always, morphologically in particular interesting, also for floodplain development, for the shallow floodplain lakes. Then the small Praila Island is still marvelous, is still one of the best preserved and most important floodplains at all at the lower Danube. The knowledge is limited, in my opinion. Here it is quite important to understand the main branch vocation. In a bifurcation or trifurcation. It's a trifurcation here. And this should be also proved or understood by means of historical analysis. And in the Danube Delta, there are, of course, many particular questions for sure. Julian can say much more about it. In my opinion, it's quite interesting or important to understand the branch vocation. So also the distribution of water into the three main branches, distribution of sediment into the three main branches, and the interconnectivity. The delta forefront is always interesting. Wilkovo, the northern delta, is of course maybe the most dynamic actually, but also in the past. So the delta is very important, and maybe also some former Liman Lake connections would be very interesting to analyze by this historical point. So from my side, I also want to offer at the end, within the project, due to my particular or complicated involvement in this project, there is a possibility even to spend additional time, to spend resources. But I have to say it is possible for middle and lower, so 2 times for middle and lower Danube, to also even to finance work in my name. Yeah, but this is working among academics, so it's not like full-time job or payments, but so this is a simple idea at the moment, so it's not fixed or something, but I would be very, very interesting to supervise, to support you for middle and lower Danube in doing so and finding nice place. So thank you very much. I'm very sorry to be too long.
Thank you very much, Uli. No, it's I'm also sorry that we're longer than expected, but it's really interesting. I'm actually happy that it is more than expected. Okay, so I propose maybe now that we move directly to the last presentation, and then after that we can have the discussion.
Yeah, do you see my slide? Okay, yeah,
Yes.
Uli, perfect. Really interesting for me. Please upload it on the cloud so that I can have. I like it to download on my computer. And yeah, it perfectly connects to my last topic for today. This is about the fluvial indicators that can be determined based on the GIS reconstructions as demanded, as proposed in the task 3.3. It's a selection we decided for the DANSER project, of course, as Uli showed already. We did a lot of different habitat-related and other analysis. But here I may have to focus on the temporal development of different water body types. We call it also aquatic macrohabitats. Then the changes in lateral hydrological connectivity between the main channel or main channel arms and the different floodplain water bodies. Then this is more or less the core analysis for the answer. Changes in fluvial dynamics, aerial erosion and sedimentation or terrestrialization rates, and then also the increase in regulation intensity and other human interventions. These are the metrics that I want to show you now. First, about the temporal development of different water body types. Here, Uli mentioned it already. The basic concept here is that of the intensity of lateral connectivity, which has a great ecological significance for migration of aquatic species, fish migration, benthos. It also determines the living conditions for macrophytes, algae, and so on. And here in this concept, here in this respect, the basic concept is that on the ecological floodplain biotopes, biotopes defined by different intensities of hydrological connectivity, based on Amorós et al. In 1987. And Uli mentioned it already. U-bottom-on, these are the lotic main arms and side arms that are flowed through all time. Then we have para-bottom-on, semi-stagnant water bodies, one-side connected water bodies. We have plesio-bottom-on, isolated, abandoned dead arms, but they are still highly influenced by the river because of frequent inundation or because of the groundwater. And we have paleo-bottom-on, remote from the river with less influence by the river, often meander oxbows. And these different biotopes or habitats are habitats for different, for example, for different fish gills, because they prefer habitats, spawning site and juvenile habitats with different intensities of hydrological connectivity, as shown by Schiemer and Weidbacher in 1992. As you can see here, for example, fish gill rheophilic A is only in the U-bottom-on, rheophilic B is in U-bottom-on, and para-bottom-on 3 is Eurodoped. Okay, they do not care so much about the different types of water bodies. You can find them almost everywhere. And stagnophilic species are in the dead arms. So this is the basic concept. And we extended the concept for habitat types of riverine landscapes, which means each type, habitat type or biotope is result of a specific process and form relationship. It reflects different stages of terrestrialization, of geomorphological development. and they are characterized by different intensities of hydrological connectivity, as already said. And here is an image from the river landscape. Ulle showed it already, from the Machland floodplain in Upper Austria in 1817, and just how we extended the concept, the new bottom on A, the main channel habitat. Then we have U bottom on B, Lotic side arms connected at two sides at low flow, more or less permanently flowed through, except for very low flow, extreme low flow situations. Then we have parabottom on A. These are side arms that blocked by sediment, unvegetated sediment bars. We have the typical parabottom on B, backwaters with only one downstream connection, and upstream it's blocked by vegetation. Then we have plesiobottom or paleobottom, and these are isolated backwaters, oxbows. We put them normally together. We do not distinguish them because we can't really say often in historical sources. We cannot really distinguish them often in historical sources. Then we have a specific focus on tributaries that join the main river, and two types of habitats, terrestrial ones. This is the vegetated area below bankful. This is what I showed in the former presentations, the light green areas, the deep lying zones of the floodplain, which is already vegetated. It can be on woody pioneer vegetation, on gravel bars, or some terrain depressions or trenches in the floodplain. Yeah, and the elevated floodplain area, this is the main niveau, the general niveau of the floodplain terrain. And this extended concept proved to be very useful for ecologists, for fish ecologists, for macrozoobenthos and so on, for macrophytes also. And each river type or river section type, like at the Danube River, if we have a meandering in south of Hungary, or in unbranching river sections, shows a different form of intensity of lateral connectivity, and different hydrological connectivity results in diverse compositions of river habitats, which means in a different biodiversity. That's the background behind that. Yeah, here's an example once more from the Lobau floodplain, just at the eastern edge of Vienna here, the situation in 1817. You see in the legend the different types of water bodies, and most of them are blue, a light blue, which means is U-bottom, which is a very dynamic, with a very dynamic float through living, space for living. And yeah, and of course, what we usually do, for each time situation you see in the x-axis, here this is for the floodplain in Vienna, not for the Lobau. We calculate based on our reconstructions the different types of water bodies, and here it's in hectare, and we see prior to regulation, during regulation, after regulation, and you see the decline of the aquatic habitats at all, and the total change, the change in the composition of the water bodies. So but for comparison with other Danube sections, we always standardize the values to hectare or square kilometer per today's river kilometer, or to refer to kilometer length of the valley axis, so to make the results comparable. We can also have a look only on the composition, not on the absolute values as shown here. You see here in the y-axis the percentage of the different habitat types. Okay, it starts at 30% here up to 100%, and we see the over time for different time periods how the composition of the water body types change. Yeah, this was to trace the changes in different types of water bodies that are important for biodiversity. And now let's have a look for the changes in lateral hydrological connectivity. You see here that once more the different colors refer to the different types of water bodies. And here we identify the other water bodies that branch off from the main river arms. Main river arms is Eupotamon A. So every connection between the main river arms and the other types of water bodies is measured here in form of the red lines. Then we sum up the length of all the indicated connections and standardize it for comparison in meter per today's river kilometer, or per kilometer length of the valley axis, or in percent of the total length of the river banks of the main channel for each time situation. Yeah, and then we see here is an example from the Morava River at the border to the Slovak Republic. The intensity of lateral connectivity here in this, here we related it to show it as a percentage of the main of the river banks of the main channel, and starting in 1703 till today, normally we see this significant decline in the intensity of hydrological connectivity, which means today we have by far less possibilities for aquatic organisms to migrate from the main river to other types of water bodies. And if we have the chance to do the same for the same river section, but for different water levels, because when we have historical water level data, like here in the Machland floodplain in the year 1812, then we can see at which water level the intensity of the hydrological connectivity, and just for mean water we can see that in 1812 approximately 1/8 of all riverbanks of the main channel show such connection, which means a possibility for migrating fish species. Yeah. Now let's go to the fluvial dynamics, which means the erosion and sedimentation and deposition. For that, first we merge all types of water bodies in each time situation. The result is in a so-called GIS multi-part polygon. And this is so-called, it refers to the active channel system. The active channel system is the water surfaces plus the unvegetated sediment bars, as I have explained before. Yeah, then we overlay and intersect the active channel system systems of each two consecutive time situations, and then we identify. Then we have to identify river channel shifts that are not captured by the temporary constructions. This is what I said after the first presentation. There was one question because of the long time periods between between historical reconstruction, then you can miss some information. And this is, for example, here, you have here the river arm, let's say in 1632, and the next time situation shows the dark blue one, the river arm in 1663. And if you overlay the intersected, the result would be then you have a gap here, a kind of island that would not be calculated. But you have to calculate this if you want to know annual erosion or deposition rates over longer time periods. So you have to identify these missing polygons or these missing areas, the orange one, and they have to be calculated as erosion and as deposition, because they were eroded when the river moved in this direction, and when in 1663 this was already once more vegetated area, the floodplain terrain. This is very important to know, to have a look on that. Yeah. Next step is the calculation of the total active channel system area per time situation. This informs us about, was the system expanding or shrinking over time? And the next question would be, what can be the causes? It is a change in the climate, and thus the change in the runoff, or human interventions. And so you typically get such an image. Here once more for Vienna, started in 1663 until 2010. It's clear that the active channel system is shrinking because of the regulation, but at nearly all rivers in Central Europe, we find the peak around 1780, also at the tributaries, Morava River and other, because this was the time of heavy climate deterioration with a very increasing flood intensity, which means the Danube adapted to the increasing flood, and the channels were widened, and it was more unbranched, more braided. And this is we usually in many rivers we can see this. Yeah. And then we have to calculate annually eroded and newly deposited areas between each two time situations. And of course, to make it comparable, we also do a standardization. For example, we calculate the annual rates as percentage of the total floodplain area, or in many cases in percent of the total vegetated floodplain terrain, so that we know how many percent of the floodplain terrain were annually eroded, newly deposited. Or when we want to see it from the other way around, from the river channels, then in percent of the total active channel area at each point in time. And so we can then show the annual net eroded or newly deposited areas. Blue would mean erosion, annual changes here in percent of the floodplain area, annual erosion, which means there are new water bodies. And the green is deposition, terrestrialization, which means new vegetated floodplain terrain. And the red one here is because of artificial excavations during the so-called second Viennese Danube regulation program. Yeah, and what we can see here in the time period up to 1780, there's an increase of erosion, which means this is because of the climate deterioration and increasing flood. The channel system widened, more erosion, as we can see here in the overall picture. Yeah, and just to make it more detailed, to analyze it, we see the annual rates of erosion and deposition areas in percent of the vegetated floodplain terrain at the respective time. The same like before, we see green, the deposition, new vegetated terrain, terrain that had developed, blue erosion, new water bodies that have developed. And you see here the time axis, and here it is calculated, standardized as percentage of the vegetated floodplain terrain. Yeah, and theoretically, if the channel controlling factors remain the same, channel controlling factors based on climate, based on land cover and the catchment and so on, the erosion should be equal to the deposition in if you look on a larger area on the longer longer time span. Of course, locally you have always disturbances and changes, but theoretically on larger scale and longer time period, it should be, the ratio should be 1:1, and this is exactly the case for 1663 to 1726. As we can see here, the ratio is 1:1. Then the ratio changed. There was more erosion because of the climate deterioration, and then was the start of local regulation measures in Vienna that disturbed the fluid dynamics. But we see here between, nevertheless, the dashed line here and here, the dashed line show the mean values between 1663 and 1825, and deposition was 0.42% of the floodplain terrain, and the erosion was exactly the same. And but you see with the amplified regulation, this values changed. Deposition is getting more and more after the regulation. There's only deposition, no erosion. And why we have here in recent time, in the last 100 years, erosion, this is not really erosion. This is because of the second Danube regulation scheme in 1972 to 1988, when the Danube Island and the new Danube were excavated. Yeah, this means natural or human-caused disturbances are reflected by significant deviations from the 1:1 ratio. Because if this would not be the case, this over longer time situations, a ratio of 1:1, the river type would gradually move towards a new river type, towards a new state. And this, of course, we nowadays see mostly due to human interventions. Yeah, finally, we also want to know quantify the human interventions. The easiest way is the regulation intensity, which is very simple, the percentage of protected or stabilized riverbanks in relation to the total length of the main channel riverbanks at each point in time. Here once more from the Morava River between 1703 and 2020. Of course, until 1820, nothing happened. Then there were local bank protections, and then the start of the systematic river regulation. And today there are 75% of the river banks are stabilized. And here, here another analysis. We will not do this in this form in DANSER, but the connects between regulation intensity in relation to other fluvial indicators. You see here in the x-axis that regulation intensity, or here called degree of generalization, from 0 to 100%, and different metrics, how they reacted with ongoing river regulation. And as you can see, the correlation was rather high between this simple, very simple metric of regulation intensity and different types of other fluvial metrics. Yeah, that's our program we have to do when we have the reconstruction finished, or we will work parallel. We will do first analysis while reconstructing the older time situations. And yeah, what's next? As already said, tomorrow, I hope that we will see some presentations for middle and lower Danube. And here it would be fine if the partners could make a short presentation. Which Danube sections are proposed for historical reconstructions? What are the reasons for the selection of the specific sections? What historical sources are available? What information on hydromorphological conditions and hydraulic engineering interventions can be extracted out? What can be seen in the maps? Then also the question is who is responsible, who would perform these studies, and then we will after each presentation discuss the information we got, for example, about the historical sources and the river section and the other questions. So that's from my side. Many thanks for the attention.